Okay, so this is another example of projectile motion. So here we have a diver leaping from a cliff, and the cliff is 30 meters above the surface of the water, and he leaves the cliff moving at 2 meters per second, but he's 40 degrees above the horizontal. Okay, so what that means, here's our cliff. Okay, we have our diver that is leaving the cliff at 2 meters per second at 40 degrees above horizontal. Okay, so this is 40 degrees right here, and the magnitude is 2 meters per second. Okay, so that's what that means. We are asked first to find the time it takes him to hit the water. Then we're going to need to find how far he horizontally travels. And then we're going to need to find his final velocity. So we kind of have to find a bunch of different things about this dive. So the first thing I'm going to do, I need to complete my picture. I need to set a reference frame. So I'm going to set it the base of the cliff, okay, to be my y equals 0. Okay, and the spot where the cliff is, that's my x equals 0. So this is my 0 point. Positive y direction is upward, positive x direction is to the left. Okay, my diver is gonna have some sort of trajectory where he goes up and then he starts coming down and he eventually hits the water, okay, at some position x, and this will be the positive x direction. At some position x away from the cliff. That's like how far horizontally he traveled. Yeah, right. In the picture, it looks like the cliff might kind of come out a little bit, which is fine. We just want to know his horizontal, how far he horizontally traveled. Okay, so my initial x position is 0 meters. His initial y position, so y naught equals 30 meters, because we are told that this is a 30 meter cliff. And we set the base equal to 0. We know his final y position, okay, in our reference frame, our y final is going to equal 0 meters. Let's see, did I miss anything? Okay, so there is our picture. I think I've drawn on my picture everything I'm given in the problem. I set up my reference frame. Now I need to inventory my variables. So let's start with the x direction. Okay, so my initial x is 0 meters. Final x, I'm going to try to find. I don't know. Okay, well, my vx, not. So my initial x velocity. I'm not directly given that, but there is a component of this initial x velocity in the x direction, in the positive x direction. And so this component here, that's going to be my vx naught. Okay, that is adjacent to the 40-degree angle. My hypotenuse would be the 2 meters per second. So I'm going to use cosine, and my initial x velocity is going to be 2 cosine 40. Okay, because air resistance can be neglected, I know that I have a 0 acceleration in the x, so that means my vx is also 2 cosine 40. And both of those are in my positive x direction in my reference frame, so they should both be positive. Okay, my ax equals 0, and the time that it hits the water, let's just call that t water for fun. Okay, so there are my x variables that I know. That's my inventory variable for the x direction. Now let's do the y direction. Okay, well, my initial y is 30 meters. Okay, my final y I know is to be 0 meters. Okay, my initial y velocity. Now I am opposite of that 40-degree angle. Okay, so my y component is here. I could draw it here, but that kind of ruins my picture. So just draw it over on the right side, which I can. So that is gonna be the sine. It's opposite of that 40-degree angle. So I have 2 sine 40. Okay, and these both have three sig figs. I'm just simplifying it and not writing all the zeros out every time. But I do know in my problem the 40 is 40.0 and the 2 is 2.00. My final y velocity, I don't know anything about right now. I maybe could solve for it. G, my gravity is negative 9.80 meters per second squared because I've set the positive vertical direction to be upward. Okay, and then the time that I care about, again, is the time that I hit the water. Okay, like we've said in previous problems, when we go to solve, we want to use the y direction to figure out the y components of our velocity. We need to use the y direction to figure out how long the person is in the air. Okay, so let's see, for A, how long does it take him to hit the ground? So we're wanting to find what this TW is. Okay, so I could use my y equals y naught plus v naught yt plus 1/2 at squared. Okay, when I plug in numbers to this, I get 0 equals 30 plus, well, my v naught y is 2 sine 40 times t plus 1/2 negative 9.8 t squared. Okay, so I could solve it with this and use the quadratic formula. Okay, but let's say I wasn't really in the mood. I wasn't feeling the quadratic formula today for whatever reason. And I realized I am going to eventually have to find the final velocity of the diver. So I could actually also first solve for Vy and then use that to solve for the time. So let's give that a go. I have shown you how you could use that first equation, but we also have the equation Vy squared equals v naught y squared plus 2gy minus y naught. Okay, and we can use this equation to solve for our final y velocity, and then once we know Vy, we could use Vy equals Vy naught plus at to solve for time. And then I don't have to use the quadratic formula. So plugging in my numbers here, well, Vy squared equals, my v naught y is 2 sine 40. We must square it. Plus 2 times negative 9.8 times my final y is 0. My initial y was 30. Okay. Plugging that into my calculator, I end up with Vy equals plus or minus, because I took a square root, 24.282766. Okay. I carried out probably more than necessary, but I do want to carry out more than just the 3 sig figs so I don't accumulate rounding error. Let's think about this. So remember we said, like in math, we always have 2 answers. In this case, we would say plus or minus. In physics, that really doesn't make sense. We have to choose whichever one makes sense for the problem. Here, we know that the diver is going to be traveling like downward, kind of like this when they come into the water. So we know that the y component of that velocity is going to be negative. So we want to choose the negative component there, and we know that Vy equals negative if we were to round 24.3. Okay, so now we can fill this in. Okay, so we solved for Vy, that's negative 24.3-ish meters per second. And now let's use that number to solve for time. Okay, so we have this equation here that we can use. If we rearrange, we get Vy minus Vy naught divided by A gives us t. And if we plug in our values, t equals, well, we have our negative 24.282766. Well, so on and so on in your calculator, right? Minus 4, well, my V naught y was 2 sine 40. I don't know why I put a 4. I was thinking 40, I think. 2 sine 40 divided by negative 9.80. Plugging that into your calculator, you get 2.609 seconds, or if we round to 3 sig figs, 2.61 seconds. Okay, so that's actually our answer for part A. Okay, it was a little bit involved, and that should be what you would also get using the quadratic formula. But I was apparently too lazy to do that today. So I knew I would actually need this value too for part C. So I was like, why not? Let's solve that, and then I don't have to use the quadratic formula. So now we actually know that TW equals 2.61. So we know that this equals 2.61 as well. So for part B, how far does he travel horizontally before reaching the ocean? Okay, so for part B, I'm going to actually rewrite. So we know x naught is 0. Okay, we want to find x. That's what we're trying to find. Okay, we know our v naught x equals vx, and that equals 2 times the cosine of 40. And we know that time of that he hits the water is 2.61 seconds, or I'll keep that 0.9 just to keep some more sig figs in there so we don't accumulate rounding error. Okay, so in the horizontal direction, there is no acceleration. So AX equals 0 meters per second squared. So our X equals X naught plus V naught XT plus, well, 1/2 AT squared is just 0. So we don't even need that part of our equation. And we have our equation for constant velocity motion. So X equals 0 plus, well, our V naught X is 4 cosine. Why do I keep doing that? It's 2 cosine 40. I keep really wanting to write 4 cosine for some reason. 2 cosine 40 times 2.609. So our X ends up being, I think, 4 meters. Yeah, so it's, on your calculator, you're going to get 3.997 blah, blah. So with this rounds, when you round to 3 sig figs, that's going to be 4.00 meters. Okay, so our diver landed 4 meters horizontally from where he began. That was his horizontal travel distance while he was in the air. Okay, the final question here asks, and actually maybe I'll go back up here. Okay, so we're asked, what is the velocity of the diver just before he enters the water? Okay, so let's kind of focus here on this point in time when he hits the water. So here's our water. We're gonna look at like just that split second before he hits. So like right here. Okay, we know that his x velocity is still that initial velocity that he began with, okay, which is 2 times the cosine of 40 is the velocity when he hits the water, or just the split second before he hits the water. Our Vy, we know we solved for, and that was the 24.3. And remember, I probably want to keep this 24.282766 when I plug it into my calculator. So we have, it's quite a bit bigger because this is about 1.5-ish, I think. And this is negative 24. So negative 24. Negative 24.3. Remember, the decimal places are like, when we put in our calculator, 282766. We'll keep those. Okay, so I know it's negative, and if I were to report that velocity being negative, so I could just report these two components of the velocity vector for my answer if I wanted. Okay, again, kind of the lazy way to do it, which would be fine, because you get the information across. So you could say Vx equals 2 cosine 40, and Vy, oh, actually we would want that as a decimal, right? Which would be 1.53. So Vx equals 1.53 and Vy equals negative 24.3. So that's what you could report for the vector. If you want that, that's perfectly fine. We could also report the magnitude and direction of this. So we could report V and this angle theta here if we wanted. Okay, so if we're gonna report the magnitude, we can use Pythagorean theorem. So we know that V squared is gonna equal Vx squared plus Vy squared. So we get V equals the square root of 2 cosine 40 squared plus 24.3 squared. And again, in my calculator, I carried out more decimal places than that, but we do end up with a velocity of 24.3 meters per second, which is kind of weird. You're going to be like, maybe I did that wrong because that was my y component. But if you think about it, if this is just 1.5 here, okay, and that's 24, like, you don't get much from this little tiny component of the x direction. It's mostly, like, the magnitude is mostly the y velocity. So it sort of makes sense. It is a slightly different, like 0.5 greater, I guess, from 0.28 to 0.33. So, or 0.05, sorry. 0.05 greater, but not a huge difference, right? When you round to 3 sig figs, it's actually exactly the same number. So our magnitude is 24.3 meters per second. And then we find that angle by taking the inverse tangent, okay? If we think about it, we could redraw our y component over here. So we're taking the tangent of that angle. The tangent of our angle equals our Vy over Vx. So inverse tangent of Vy over Vx is going to end up being 86.4 degrees below the horizontal. Okay, so we could alternatively report both the magnitude and direction. So either of those works, either just the components or the magnitude and direction would work for part C. Okay, this problem is a good one to kind of look at and review because it kind of addresses a bunch of different things that you could see in a projectile motion problem. Hopefully that was helpful. And yeah, that's all I got.